Bismillahirrahmanirrahim. In this video, we'll talk about bipolar junction transistor circuits at DC level. Now, before we start the actual discussion, let's just recall that if we have a circuit like this, the transistor parameters, then these three terms I am sure you know by now, but we'll just repeat. This is with respect to ground. This is VBE, that is the voltage at this point with respect to emitter. This is emitter of an NPN transistor. So this is VBE, and this terminal is positive and this is negative. Then we have VCB from collector to base. So collector is positive and base is negative in this case, and this will be called VCB. And the third we have VCE. So collector is positive and emitter is negative. Generally this is convention followed, that the first term represents the positive terminal, so base here is positive and the second term is negative. Here collector is positive and second term B is negative, and here also collector is positive and emitter is negative. And the three currents, the base current and the emitter current and the collector current. Also, an important point that we have to remember is the value of VCE. If the value of VCE is 0.3 volt or more, then we call the transistor to be in the active mode. So this is the active mode here. This is the region for active mode. This is VCE. So if it is greater than 0.2 or let's say 0.3, then this we are sure that this is in the active region. So VCE at 0.3 is called edge of saturation. So this is the saturation point. So at 0.3 it will be at the edge of saturation, and greater than 0.3 it will be in the active region. And if VCE is 0.2, then we call that the transistor is operating in the saturation mode. Sometimes you need to find the corresponding value of VCB for being in the active mode or in the saturation mode. So we can just write by KVL from here, negative VBE, so negative VBE, negative VCB, negative VCB, and positive VCE equals to 0. And from here you can see that VCB is negative VB plus VCE. Now, as we have discussed here, that for active mode, VCE should be 0.3 or greater. So we plug in the value of VCE 0.3. VBE, we know it is 0.7. So we plug in that value. So VCB, if it is minus 0.4 or minus 0.3 or minus 0.2, etc., then it is operating in the active mode. But if we plug in this value for the saturation, VCE is equal to 2, and then we'll get an answer of minus 0.5. So if VCB is minus 0.5 or greater in the negative, that is minus 0.6, minus 0.7, then we'll say that the transistor is in saturation mode. So you don't have to really remember this. If you just remember this, then you can easily calculate the value of VCB and for active mode and saturation mode. Okay, now in this lecture we'll take three cases. This is the first one. Here the base voltage is positive 4 volt. Then the same circuit we'll repeat. This is with base voltage positive 6 volt, and the same circuit again with the base voltage 0 volt or grounded. So we'll see that this will be the active mode scenario, and this will be the saturation mode scenario, and this will be cutoff mode scenario. So we'll do all these problems. Example 6.4 is for active mode, 6.5 for saturation mode, and 6.6 is for cutoff mode. So just by changing the base voltage, we can move from one mode to another mode. Okay, now as will be seen that in analyzing a circuit, the first question that one must answer is, in which mode is the transistor operating? In some cases, the answer will be obvious, as we have discussed that if you know the polarity of the voltages, we can determine whether it is in the active mode or saturation mode or in the cutoff mode. The answer will be obvious. A quick check of the terminal voltage will indicate whether the transistor is cut off or conducting. And we'll take help of this diagram. You can see in the cutoff mode, both are reverse bias, both junctions, that is this junction, base emitter junction is reverse bias, and collector base junction is also reverse bias. Whereas in case of an active, this is forward bias, the base emitter, and collector base is reverse bias. And in the saturation mode, both are forward bias. This is also forward bias and this is also forward bias. Okay, the answer, however, can always be determined by utilizing the following procedure. So you keep in mind this procedure. Assume that the transistor is operating in the active mode. So that is the first assumption we have to make. And proceed to determine the various voltages and currents that corresponds to this active mode. And after we have determining the voltage and current, then we check for consistency of the result with the assumption of active mode. So we'll check whether it conforms to the active mode parameters or not. That is VCB of an NPN transistor greater than 0.4 volt? So we saw in the previous, we found out it to be 0.5 or 0.4, then this is in active mode. If the answer is yes, then our assumption is complete. If the answer is no, then we assume it to be in the saturation mode and proceed to determine the current and voltages and then check for consistency of the result. Here the test usually is the test is usually to compute the ratio of IC over beta and to verify that it is lower than the transistor beta. So this is called, in the saturation mode, the beta is called beta forced, and if beta forced is less than the transistor beta, then it is operating in the saturation mode. Okay, so let's have our first example. This is the circuit, 4 volt power supply. You have to analyze the circuit to determine all node voltages and branch currents. Assume beta to be 100. And we'll follow this sequence. First of all, we'll find VE, then we'll find the current IE, and then we'll find the current IC, then VC, and finally IB. Okay, we note that the base is connected to plus 4 volt, so this is connected to plus 4 volt, and the emitter is connected to ground through a resistance RE, so this emitter is connected to ground, and therefore it is safe to conclude that the base emitter junction is forward biased. So this is a higher potential and this is lower potential, so this is forward biased. And we can assume VBE to be 0.7 volt as we have learnt. So VE, this voltage VE is, if you take this loop, this is the voltage VE with respect to ground. So we can say that it is 4 minus this drop here, VBE, is equal to VE. So VE okay, we know VE is 3.3 volt. So actually VE is the drop across this resistor. So we can say that the drop across resistor is IE into RE is equal to VE minus 0. And from there we can find out that IE is VE minus 0 divided by RE. So 3.3 and RE is also 3.3 kilo. So the answer becomes 1 milliampere. So we got the second point. Now we'll evaluate the collector current IC by using this formula. IC is equal to alpha IE. And I hope you remember there's a relation between alpha and beta. So alpha can be written as beta divided by beta plus 1. So putting in the value of beta, alpha is 0.99. We already know IE. We have now calculated alpha. So we can find the collector current IC to be 0.9 into 1 is equal to 0.99 milliampere. So third we found. Now let's see the fourth point is the VC. Now VC, when we say VC, it is with respect to ground. So we can say that this voltage 10 volt VCC, actually this is called VCC, minus this drop in the RC resistance is equal to VC. So VC is 10 minus ICRC. We have all the parameter values, and therefore VC is 5.3 volt. And now lastly, this current IB. Now, since the base is at plus 4 volt, this is at plus 4 volt, and VC is at 5.3 volt, the base collector junction is reversed bias by 1.3 volt. Okay, now if you look here, this is at higher potential, VC is 5.3 volt, and VB is 4 volt. So that means this is at higher potential, and so this is a reversed bias. And therefore the transistor is indeed in the active mode. So we know that for active mode this has to be forward bias and this has to be reverse bias. So the transistor is in active mode. So that is confirmed. Now let's find out IB. So IB, if you look at the circuit, IE is equal to IB plus IC. So IE is equal to IB plus IC. And we know IC is beta IB. So beta IB. And therefore from here we can find IB to be IE divided by beta plus 1. From here, if you take IB common, it will be beta plus 1. So it comes here. And plugging in the values, we find the value to be 0.01 milliampere. So this way we have found all the 5 parameters, and we have also confirmed that this is indeed the transistor is operating in the active mode. Now let's see the next example, example 6.5. Same circuit. Now this voltage has been changed, and the transistor beta is specified to be at least 50. Now just for comparison, you remember this was the last case or previous case. Now it is 6 volt, and we need to determine again all the node voltages and branch currents. Now this time we'll follow the similar technique. First we'll find VE, then we'll find this current, and then we'll find VC, IC, and IB. Same way that we did before. With 6 volt base, the base emitter junction will be forward biased. So we can say that VE is 6 minus VBE. So 6 minus VBE, 6 minus 0.7 is 5.3 volt. So VE is now 5.3 volt and IE is 5.3 divided by 3.3 is this resistance. So IE is 1.6 milliampere. Okay, now assuming, as we had mentioned, first of all, you just assume that the transistor is in active mode. So we are assuming that the transistor is in active mode, and therefore IC should be alpha IE, and this could be approximated to be equal to IE because we know the value of alpha is 0.99, so which is almost 1, and that is why we can assume that IC is equal to IE. So for VC, this voltage VC will be 10 volt minus the drop here. So VC is 10 volt minus the drop across ICRC, 4.7 into IC, and IC is from here, it is actually IE, which is 1.6. So plug in that value. So VC is 2.4 volt. And now look here what is happening, that the base is at 6 volt and the collector is 2.4 volt. That means this is now forward biased, negative to negative and positive to positive. So this is forward biased and base emitter is already forward biased. Therefore, this transistor is not operating in the active mode, rather it is operating in the saturation mode. Since the collector voltage calculated appears to be less than the base voltage by 3.5 volt, it follows that our original assumption of active mode operation is incorrect. In fact, the transistor is in the saturation mode. Now in the saturation mode, the voltages VE and current IE will remain unchanged. So this will remain unchanged. The collector voltage, however, will change and it will become, now the collector voltage, this one, is this voltage VE plus the drop here, and since it is in saturation mode, so we'll call it VCE sat, saturation. And we have also learned from here that VCE is 0.2 volt in the deep saturation mode, so we'll take 0.2. And so our VC is actually 5.5 volt and not as we calculated earlier, it was 2 point something. So now that we know VC, we can find this current IC, 10 minus VC. So 10 minus VC, 5.5 divided by the resistance. So 0.96 milliampere. All these values. And IB again can be found from IE minus IC. IE is 1.6 and IC now we have found it to be 0.96. Therefore IB is 0.64 milliampere. So we found all the parameters and we also confirmed that this is operating actually in the saturation mode. Now the transistor is operating at forced beta, and forced beta is IC over IB. We know IC is beta times IB. So from here, B forced will be IC over IB, and this is 0.96, 0.64, so 1.5, and this is forced beta is less than the assumed beta, which was 50. So this is okay. Since B forced is less than the minimum specified value of beta, which was 50, the transistor is indeed in the saturation mode or saturated. Now the final example 6.6. Now this is the circuit, and just for comparison, these were the two that we already solved. In this case, the base is connected to ground. Now since the base is at 0 volts and the emitter is connected to the ground through RE, so base is at 0 volt, and this is also connected to ground, the base emitter junction cannot conduct, and the emitter current is 0. So there will be no current flowing through this. We can also say that since this is directly connected to ground and this is connected to ground through resistor, therefore this will be at a higher potential. So we can say that the base is negative with respect to the emitter. So this is also a sign of reverse biasing. So this is reverse bias. Note that this situation will obtain as long as the voltage at the base is less than 0.5 volt. So this is 0, but even if it goes up to 0.5 volt, this will remain in the cutoff state, because you have to have a 7.7 drop here. So from here, this is still at the higher potential by Now the collector base junction cannot conduct, being reverse bias. Now this is 10 volts, so this point will also be at some positive value, and this is ground. So this is also reverse bias. N is positive, and base is collector is positive and base is negative. So this is also reverse bias. So this is ensuring that this is in cutoff mode. The transistor is in cutoff mode of operation. The emitter voltage will be 0 since the voltage drop across RE is 0. So there will be no emitter voltage because there is no current here, no drop here. And the collector voltage will be 10 volts since the voltage drop across RC is 0. So the collector voltage here, this will be equal to this volt because there is no current IC, and since there is IC is 0, therefore the drop here is also equal to 0, and therefore VC is equal to 10 volt. So I hope this gives you an idea as to how the variation in base voltages can make the transistor operate in active mode or saturation mode or cutoff mode. Thank you.